Welcome back. Let's begin 11.3 and 11.4, integral test and comparison test. In these two sections, we confine ourselves to positive term series, where each term is positive or at least non-negative. We can add some zeros, but that doesn't affect at all. So positive term or non-negative term, those are pretty much the same, theoretically speaking. Before that, however, let's do just a little bit of review. We talked about series, and that's basically a sequence of partial sums. It's not so important, so I de-emphasize it in gray. Now the next one is important, the nth term test for divergence. If the series converges, then the general term must go to 0. Equivalently speaking, if the general term does not go to 0, then the series does not converge or it diverges. So this testing can apply when a series diverges. It cannot be used for convergent sequence. The limit of the general term going down to 0 does not necessarily imply the series converges, as you can see in this example. 1 over n certainly goes to 0, but this series diverges to infinity. Now the proof of the nth term test for divergence is actually easy. Write down the partial sum, subtract one from the other, then we have general form. Apply the limit rule, then Sn minus 1, they both go to 0, go to s, so we have s minus s going to 0. There goes the full proof. And then let's talk about geometric series. And geometric series formula is very, very important because this is one of really rare type of series that we can precisely calculate. And here it is. The first term over 1 minus r. That's when r is less than 1 in absolute value. Otherwise, we must have divergence. When r is greater than 1 in absolute value, the general term a, r to the nth power, will not go to 0, so the nth term test for divergence applies. Now what if r is less than 1? Well, we have something like this. Here's Sn, and then here's r times Sn, and then the middle terms, all these middle terms will just cancel each other, and then I'm going to get only first and last term if I subtract one from the other. Factoring Sn out, we're going to get next formula, and then dividing by 1 minus r. Finally, here we go. Sn is equal to that, and this is the geometric series formula for finite geometric series. Now when r is less than 1 in absolute value, this term here, r to the n plus first power, go to 0. So we have the desired formula right over there. When r is not less than 1 in absolute value or greater than or equal to 1 in absolute value, r to the n plus first power does not go to 0. Actually, it does not even converge at all. So we don't have anything. Next, a little bit less important type, telescoping series. Well, maybe I shouldn't have de-emphasized in gray. Okay, maybe not that important, as important as geometric series, but of moderate importance, yes, we have to assume that. Decompose the general term in partial fraction, and then write down several terms and use the cancellation. That's what the telescoping series does. Okay, that was the review, and let's move on to integral test. Oh, just one more thing. Before that, let me mention one thing. Integral test and then comparison test are both about positive term series. We'll just keep adding positive numbers. Consequently, the sequence of partial sums is increasing. So the monotone sequence theorem applies. Bounded increasing sequence converges. And if it is unbounded and the series goes to infinity, if it is bounded, then it converges. So I don't have to consider oscillation or things like that. just less than infinity or just going to infinity. That's all I need to know. Now here you go, the integral test. What is an integral test? If we have a eventually decreasing function, positive and decreasing function, continuous positive and decreasing function, and an is f of n, then the series converges if and only if the integral converges. And the behavior of the series and behavior of the integral are pretty much the same. Well, it's difficult to understand without pictures, so let's study it with picture. Here we go. Here we are looking at a graph of a eventually decreasing continuous positive and eventually decreasing function. It doesn't decrease from all the way from 0 to infinity, but after a while eventually it decreases. So we have 3 white rectangles which do not really play any role because for several terms that's finite anyway, and all these pink rectangles, from that point on we have decreasing function, so everything is okay. And the sum of the areas of all these pink rectangles here is less than the integral calculated from m to infinity, and that's less than infinity, then the tail part of the series should be bounded. And then we can apply that monotone sequence theorem, monotone's non-negative series theorem, whatever you may want to call, and conclude that the series converges. Now, what if the integral diverges? We're going to have a situation like that. All you have to do is shift all those rectangles to the right by 1. Please note that we have the same blue curve here, but we have 3 white rectangles for the first picture, but only 2 white rectangles in the second picture. And then all those rectangles are actually shifted to the right. And then what do we get? Because of this decreasing nature, the sum of the areas of all those pink rectangles is greater than the integral. When integral is infinity, then the series, the tail part of the series is infinity as well, because that's even bigger. So there goes the proof. If the integral is infinity, then apply this picture and conclude that series is infinity. And then integral is finite, then apply this picture, and then you conclude that tail part of the series is convergent. Okay, now that we talked about the theoretical background of the integral test, actually we completely proved it. Let's talk about the most important example of integral test. As a matter of fact, this is the reason why we are doing integral test before anything else, in order to get the p series. When p is greater than 1, then series given by 1 over n to the p power is less than infinity, so it's convergent. Bounded, increasing, so convergence. When p is less than or equal to 1, then divergence. Proof is pretty simple. When p is equal to 1, we have a logarithmic function, so we have to have an infinity. P is not 1, then we have this power function. Depending upon what you want to write, we have these 2 identical equivalent expressions. Well, this latter expression is a little bit more convenient when p is greater than 1, and plug in infinity, that goes to the denominator, so you can see convergence. And the first expression is more convenient when p is less than 1. In that case, plug in infinity there, then you have infinity numerator, so you see the divergence. In short, we have this conclusion. Now let's work on some examples that can be done with integral tests, and the very first example is, well, the most typical, maybe the only worthy example for integral tests, maybe. It kind of goes like this. Take this function 1 over x log of x and integrate it using integration by substitution. Here we go, y as log of x and dy is 1 over x dx, and then rewrite this integral and then this y integral show up, we have 1 over y. So the antiderivative is log of y, and we have infinity. So what does it tell me? Well, the series diverges too. The second problem is pretty much the same as the previous problem. We use the same substitution, and we end up with same substitution here. We end up with 1 over y squared. So we have negative 1 over y as a antiderivative. So plug in those values. Infinity goes to denominator, so we have finite value. So what does it mean? Integral converges, so the series converges. The third example is rather, what can I say? This is not really practical, but it can be done with the integral test. And this is really inefficient because actually this series converges no matter what power we have. Even if we have n to the 2000 power there, we still have to have convergence. And that kind of thing will be answered by comparison or limit comparison test. But for integral test, what we can do is relatively limited because the integral should be computable. And in this case, yes, we could, because we could use integration by substitution like this, and then we have an antiderivative, and computation follows here. But I must warn you, except for very special cases like, well, this one, most typical, and pretty close to the first one, kind of like these, A and B of this example 3.3, and the kind of examples that you have to use integral test is rare. And if you have something really complicated, usually it means don't use integral test, because calculating that's integral of something complicated is pain in the rear end. You don't really want to do that. Okay, the final topic is the remainder estimate, and this one is far less important comparatively speaking, but let's talk about it anyway. I may end up writing an exam problem here. Less likely, I have to admit, but well, who knows, I may. Goes like this. Remainder can be estimated by integral, and then integral from n plus 1 to infinity versus integral from n to infinity. They're kind of like, let me see, where's the picture? No, not from this picture. Do I have picture over here? Oh yes, I do. Okay. The red part, this tail part of the series, is depicted by these pink rectangles in this picture. And the integral from n plus 1 to infinity is a green curve, or area underneath the green curve. An integral from n to infinity, that's blue curve. And as you can see, let's see, integral from n plus 1 to infinity, so you're calculating the integral when what is the n value here? We have 3 white rectangles, 1, 2, 3. So in this case, we are calculating this tail part of the series from k equals n plus 1, which is 3 plus 1. So the series begins from a4 plus a5 plus a6 and so on and so forth. And then this integral, blue one, calculates the integral from 3 to infinity. This one calculates from 4 to infinity. And well, as you can see from this picture, blue integral is above those rectangles, green curve is below those rectangles, so we clearly have this inequality relation. So we can estimate the error, which is the difference between the series and then first several terms, or in other words, the tail part of the series, by calculating the integrals and estimating kind of like this.